if you can hear me clearly. Is everyone hearing me clearly?
Yes.
Okay, so I want to welcome you to my lecture today. And of course, today the focus is basically going to be on another exciting statistical topic. Today I'm actually having lecture on Zoom because of the fact that I have a little emergency, but that's has actually been under control now. So tomorrow I'm actually going to return to in person. Okay, so once again, I want to welcome you to this lecture. This is a new week, okay? And of course, the practice questions is basically going to be released today, okay? Please make sure you check the announcement section, okay? The practice question for the midterm and the information about the midterm will actually be released today. So like I said, once again, I want to welcome you to this lecture. Okay, so give me 1 second. I'm going to, share my lecture slide. Okay, so need you to confirm if you are seeing my lecture slide. Is every okay? You can see it. Thank you so much, and thank you for confirming that. Okay, so so before I go into Poisson regression, I think I'm basically gonna have a kind of recap on what we've done before, so that you will be able to understand, what we're doing. Okay, so before I move on, can you confirm again if you are hearing me clearly?
Yeah, we can hear you.
Okay, thank you so much. Thank you for confirming that. Now, when we are trying to characterize relationship between variables, okay, we normally want to put into consideration the nature of the response variable. The nature of the response variable is what is basically going to determine the regression type model that we're actually going to use. Now, when I'm seeking to characterize relationship between variables and the response variable, I mean the outcome variable, the one you also call dependent variable, if it is continuous, we use linear regression. We're going to specify linear regression, okay, provided all assumptions of the linear regression hold. Now, in a situation where the response variable is categorical, categorical, where we're actually talking about situation where the possible outcome is true, okay, then we're going to use what I call the binary logistic regression. Okay, now what of in a situation where the levels of the response is more than 2 and they are not ordered? If they are not ordered, we're basically going to use multinomial logistic regression. Okay, now if we have the levels of the response variable when we are seeking for a relationship and the levels of the response variable is more than 2 and they are ordered, okay, they are ordered, okay, we're basically going to use the ordinal logistic regression. Okay, now I remember the one we did on Thursday. What if in a situation where the range of the response variable, the level of the response variable is bounded between 0 and 1? Okay, with such a way that it's greater than 0 but less than 1. Okay, where we have something that has to do with the proportion rate, percentages, and the like. Of course, we're basically going to use beta regression model. But you know what is new today? What is new today is what of in a situation where I'm actually seeking for relationship between variables and the response variable is not continuous, it's not categorical, it is not a rate, it is not a proportion, it is not a percentage, but it is a count. Okay, it is a count. Okay, you know, this is what I mean, count. Okay, it is a count. Okay, so when you're talking about count now, okay, then every other regression type that we've done is, they are not going to be appropriate. So what's going to be appropriate is what we're going to call Poisson regression. Okay, so the takeaway now is what actually determine, the regression type model I'm actually going to use depend on the nature of the response variable. So because of that, I want to welcome you to another class of regression that we call Poisson regression. Okay. Now I'm going to walk you through an example of a Poisson regression now. Okay. The number of persons killed by mole or horse kicks in the Peruvian army per year. Let me tell you this. There is a particular distribution in statistics that we call Poisson distribution. Poisson distribution is going to be underlying distribution in the Poisson regression model. You remember before now, when I'm talking about linear regression, the underlying distribution of the response variable is basically going to be normal. When we were talking about, logistic regression, particularly when we're focusing on the binary logistic, the underlying distribution was binomial. Okay, when we were focusing on multinomial logistic regression, the underlying distribution was actually multinomial. But right now, and you remember when we're focusing on the beta regression model, the underlying distribution was a beta distribution. Right now, we are focusing on a Poisson regression model. The underlying distribution is going to be Poisson distribution. In statistical theory, we apply Poisson distribution in a situation where there is a rare occurrence of an event. Okay, take a look at this. It's okay, rare. Okay, we use that to model rare events. Okay, that's exactly what we use that to do. I'm going to write that again. Okay, give me 1 second. Let me check my, give me 1 second. I'm going to see. Okay, I'm taking my pen now. Okay, rare. Okay, so rare events. Okay, we use Poisson regression. We use Poisson distribution to model rare events. When you talk about rare event, you are talking about event that occur in a blue moon. Now we are talking about the number of persons killed by a moon. That's a rare event. Or the numbers of horse kicks in the Prussian army per year. That's a rare event. We're talking about the incidence of a particular, disease. Okay, that's kind of rare. You get what I mean? Okay. Now, another example now, okay, is basically the number of people in the line in front of you at the grocery store. Okay, because we basically want to investigate the effect of some factors on this. What determines when I go to grocery store, maybe I actually go to Target or Walmart and the like. Okay, and I want to check out. Okay, so what determines the number of customers that are actually going to be in front of me. I'm not going to be the only one, that is actually visiting those stores. Okay, you understand what I mean? So give me 1 second. I think some are asking me to do something now. Let me see. Give me 1 second. I'm actually gonna see if the facility to do all of that is actually here. Give me 1 second. Okay, so I think everyone, you can all hear me clearly, right?
Right.
Okay, thank you so much. Thank you for confirming that. Okay, so now if you take a look at that, the predator may actually be, include the numbers of items they currently offer at a special discounted price, because what we attract customers to go to a restaurant, to a particular store, maybe that particular store actually offers some discounted price. Of course, we all know how consumers behave. Okay, now another reason may be whether there's a special holiday. You get what I mean? Okay, whether there's a special holiday, okay, or you have a very big sporting event. Okay, a very big sporting event, could be a football game and stuff like that. Okay, so there's several factors that could actually lead to that. I remember what normally happen in Black Friday, where a lot of stores will offer discounts on their products, and of course a lot of customers will be attracted in the process. Now another example is going to be the numbers of awards hand by students at one high school. The predator of such award, it may include the type of the program, okay, whether it's into vocational, general, or academic, and the score on the final exam in maths. All these fall under count data. These are not continuous. We're talking about number. Take a look at that. We're talking about number. That's a count. Okay, that's a count. If you take a look at all of that, so situation where the response variable is a count. Okay, we're basically going to use the idea when we are seeking relationship between predators and a response variable that's a count, we're going to use Poisson regression. Every other type of regression is not going to work. Okay, we put into consideration the nature of the response. Okay, so I'm going to move right now. The next one, those are the examples, right? Now, there's something I want you to see. We want to look at the relationship between the Poisson regression we're doing now to other type of regression. Okay, now if like I said, if you take a look at what I put here, okay, take a look at this. Both logistic and Poisson regression are types of linear models. Okay, take note of that. They are general, they are actually classified under that. Okay, they are type of linear model. Okay, now they extend the idea of linear regression with a continuous outcome. For the case of binary outcomes, we actually fit a logistic regression. And for the case of when you have a count data, we're going to fit Poisson regression now. And let me tell you this. The link function is what is going to be different. I need you to take a look at this now. Okay, when you have a linear, the distribution is normal. I told you the other time. Before you can actually fit a linear, it means the nature of your response variable is continuous. Okay, and the link function is going to be identity. Identity is just going to be, okay, I'm only going to be focusing on mean equation, mean equation. That's going to be identity. That's going to be link function for linear regression. Now the logistic that we have done, okay, I'm talking about the binary logistic. Okay, the link function is going to be logit. You remember what do we call logit? The logit is the log. You remember the log of the odd ratio. That's what we mean by logit. Okay, what we mean by logit is the log of the odd ratio. So the link function that we use in the logistic regression is different from the link function that we use in the linear regression. In the linear regression is identity. Identity. That's what we use. Where the f of mu equal to mu. But in the case of, so the pi here is what I call p here, okay, which is going to be the proportion of, one of the level of the categorical response. And now that I'm actually focusing on Poisson regression, okay, another name for Poisson regression is what we call log linear. Log linear. Log linear. That's another name for Poisson regression. And you're going to see the reason why, because it's using the log. It's using the log as a link function. Okay, you're actually going to see what we're going to do at the end of the day when we're applying log, Poisson regression. We're basically going to say that we're going to be talking about, we're going to be using log in doing that. Therefore, the length function is going to be the log of p. I needed to see the difference between the, the link function for logistic and the link function for Poisson regression. Take a look at. They are not the same. Okay, so take a look at that. Okay, now the next thing I want to show everybody now, if I basically want to write the model, okay, the model for, for Poisson regression, I told you the other time, we're actually going to have a log, the log of what? The log of the expectation of the response variable. And that very log of expectation is going to be equal to the log of lambda ij. What is a lambda ij? The lambda ij is basically what I'm actually going to call the predicted rates. Okay, if you want to talk about customer visiting your store, you're basically talking about the rates at which customer visit your store. If you want to talk about, the numbers of people killed by snake bites in a year, you're actually going to be talking about that rate, which is going to be the lambda ij. So we're going to have a contingency table that you're actually going to see that the lambda ij is going to be the predicted rate for the ith row and jth column of that contingency table. And there's going to be another lambda that we're going to call a baseline rate. So what I'm trying to say in essence now, okay, the Poisson regression model is basically going to have what I have here. Okay, now what is alpha now? The alpha is basically going to be the effect that we're actually testing. Okay, so I'm going to give you the further interpretation of all of that. Now, if I really want to go more, this is what I'm trying to say. The alpha I, okay, is the rate ratio, which is the effect of being in row I compared to the baseline. Okay, and what is a yj? That is a rate ratio, the effect of being in column J compared to baseline. Okay, and of course, we're basically going to have the rate ratio, which is the factor by which the baseline is multiplied to get a rate, where I call the expected set count. But you know what? For you to be able to understand how Poisson regression model is applied, I'm actually going to walk you through an example right now. But before I move forward, I need you to confirm again if you are hearing me clearly.
Yep, we can hear you.
Thank you so much. Thank you for confirming that. Okay, so I want to talk about, let's take a look at this. We got an outcome variable y, which is the numbers of customer visiting store from region. Okay, and what are the predators? Okay, the predators are x1, the numbers of housing units in that region, and x2, the average household income, S3, the average housing unit age in region, and S4, down to nearest competitor, and S5, average distance to store in miles. Okay, so you can look at the response variable now. The response variable is number. Okay, look at number, right? Because of the fact that they mention number, we're basically going to use a Poisson regression model. Because we apply Poisson regression model in a situation where the nature of the response is a count. A number is a count. And right now, we basically want to look at the effects of these 5 explanatory variables on the numbers of customer visiting store from region. And of course, we're going to use 110 regions. Okay, the observation here is regions. Well, we're going to use 110. Okay, I needed to take a look at all of that. Okay, what I'm trying to tell the world, you cannot use any model other than Poisson regression here. You cannot use any model. Otherwise, you're basically going to mislead. Okay, now, based on this data set, how am I going to write regression model? The fitted regression model. Okay, this is what I'm going to write. I need you to pay attention. This is the model. You see the way I wrote the model now. The difference between this and the multiple linear regression, in the multiple linear regression, instead of having this guy, we're only going to have y, right? That is the difference. So if you put a y, you are wrong for Poisson regression. For Poisson regression, you're going to write log lambda high equal to all of that. Of course, we got x1 to x5. Does that make sense? And what you see now, okay, the probabilistic component of the model. Let me tell you this. Every statistical model has a probabilistic component. You remember the other time when you specify the probabilistic component of a model is basically talking about the error in the model, and the distribution of the error is the distribution of the response variable. The response variable here is count, is actually going to follow Poisson distribution, and that is exactly what I'm trying to say here. So which means yi, the outcome, given any of the predator, we actually follow Poisson distribution with parameter lambda high. So why do we have lambda high? The lambda high because, we have different kind of predator. Take a look at all of that. Okay, now that is the specification. Now this is the data set. Okay, the false 9. Okay, in the data set, don't forget, we're actually using 110 data set from 110 region. Okay, we're focusing on looking, trying to figure out, okay, the effect of the housing income, age, competitor, store on the numbers of customers that will visit a store. Oh my God, if you take a look at this is a count, right? That's a count. That is going to be the response variable. That's your outcome variable that we also call dependent variable. So these guys, so this is y now, and this guy here is x1, this guy here is x2, okay, this guy here is x3, okay, this guy here is x4, okay, and this guy here is x5. So take a look at that. Okay, so we actually want to use a Poisson regression in trying to investigate the role of housing, the role of income, the role of age, the role of competitor, and the role of store on a number of customers that will be visiting a store. Okay, I needed to take a look at that, and we are actually using, regions, like 110 region. That's what we're using. Take a look at all of that. Okay, now the very first thing we're going to do, we need to first tell the world the reason why we cannot use linear regression for that. The reason why we cannot use linear regression is because there's going to be a violations of assumption of using linear regression. One of the assumptions of linear regression is normality. Normality. Okay. Okay. So one of the assumptions is normality. Okay. One of the assumptions of linear regression. So what I'm trying to tell you now, the normality assumption will be violated when you use linear regression. Okay. Now, if you want to test that, you can try to generate the histogram of the customers. The customers is the response variable. Don't forget the probability distribution of the response variable is also going to be the same as the probability distribution of the error, which we expect that it should be normal, right? But if you take a look at what I'm displaying now, this is not normal. Okay, this is skewed. And Poisson distribution is skewed. I need someone to confirm again if you are still hearing me clearly. Is everyone still hearing me?
Yep.
Okay, thank you so much. Thank you for confirming that. And that was why I'm trying to say here the customer account distribution is clearly not normally distributed. Take a look at that, judging by the histogram. And therefore, because there's a violation of assumption, the linear regression is not going to work well. And what is going to work? What is going to work is going to be the log linear regression. The log linear regression, I told you, is another name for Poisson regression. Okay? That's another name for Poisson regression. Another name for Poisson regression is what we call the log linear regression. That is going to work. Okay? That is basically going to work because the Poisson distribution is skewed. Okay? It's kind of skewed. Okay? And we are working with a CAM data. Okay, now you know what I want to show you now. I basically want to show you the code now. I need you to pay attention to the code. Oh my God, take a look at the code now. If I'm looking, I'm actually going to write GLM. Okay, customers. Why am I writing GLM? I told you the other time, Poisson and logistic regression, they actually belong to the family of that linear model, but general linear model. That's why you see GLM here. In the case of logistic regression, we normally put GLM as well. The difference is just going to be in binary logistics, we're going to say family equal to binomial. But in the case of Poisson, we're going to say family equal to Poisson. Can you see the difference? That's exactly what I mean. Okay, this is the output. Oh my God, this is the output that we have now from the Poisson regression model. Okay, that we just actually conduct now. Oh my God, look at the p-value for housing, for income, for age, for competitor, and for the store. They are all statistically significant. They are all statistically significant because their p-value is less than 0.05 level of significance. So this is an output for Poisson regression. So take a look at that. Okay. Now, you can all see now that the Poisson regression that we fitted, we're trying to test the effects of a particular predator, housing, income, age, competitor, and store. And they turn out to be significant, as you can see here. Okay, the p-value that we got, the p-value associated with age regression coefficient is actually less than 0.05. Take a look at that. Okay, so because of that, the predator here, okay, they're actually significant. Okay, which means they actually play a significant role in predicting the numbers of customers that will be visiting store from region. And that is the reason why, the manager, need to actually put this into consideration if they basically want to attract customers. Okay, so another thing I'm going to talk about now. This, from the estimates that we got, Okay, what of if I ask you to write out the fitted model? Your fitted model is basically, don't forget, for the way we specify our Poisson regression model, we've specified that in a log linear way. Take a look at that, the log of lambda I, okay, equal to that. You see that? That is the specification. So, well, what I'm just going to do is to go back into the table and just plug in the values of the beta naught, beta 1, beta 2, beta 3, beta 4, beta 5. As you can see, the values here. Okay, now the beta naught now is actually this guy. The beta 1 is this guy. The beta 2, the beta 3, the beta 4, the beta 5. That is exactly what we have. Take a look at that. You see that now? Don't forget what X1 stand for, housing. X2 stand for income. Okay, X3 actually stand for age, and X4 stand for competitor, and X5 stand for store. Take a look at that. Any question about what I just displayed right now? Any question on how I figure out, my fitted Poisson regression model? Any question? Can you see if you get that clearly? I need you to say yes, or you comment yes, or you give me a thumbs up if you really understand that. Oh my God, I got a lot of thumbs up. Okay, but you know what? If there's anyone among you, oh, I got a lot of thumbs up, and there is a chat too. Oh my God, I'm super excited that you all got that. Like I said, statistics is very, very easy. Okay, very, very easy. All you just need to do, take your time, try to understand the nature of the response variable, you know, before you can actually fit, an appropriate regression type model, when you want to characterize relationship. Okay, so take a look at that. Okay, log, you can see what I wrote. This is a feeder model now. Okay, this is a feeder model, and this is the formula that I use. Okay, and you need to take note of all of that. That is how we specify Poisson regression model that we also call the log linear regression model. Don't forget that. Another name for Poisson regression model is a log linear regression model. Okay, take note of that. Okay, so the next thing I actually want to do now, when you actually fitted a model, the next thing you're going to do is how do we interpret parameters in our model? For instance, how do you interpret a beta naught? Okay, how do you interpret this guy here? How do we interpret that? Okay, so if you want to interpret that now, I said that's a baseline log expected count. Look at what I said. Log expected count, okay, or we're going to call that log rate in the group with all covariate, okay, all the covariate, they're going to be equal to 0. You remember the way we interpret the intercept mathematically? The values of y when s equal to 0. Right now, we're trying to say 2.94 actually represent the baseline log expected count, okay, when the housing, income, age, distance to the nearest competitor, average to the distance store, okay, they are all set as 0. Take a look at all of that. That's what I mean. Okay, so you can see I'm actually using log. You remember in binary logistic regression, when you want to interpret the parameter in the binary logistic regression, they actually call log odd estimate. Do you remember that? Log odd estimate. But right here, we're basically going to call them log. Okay, like for instance, it's a log expected count. Okay, now if I don't want to talk about, if I want to remove the log, what am I going to do to remove the log if I only want to focus on the expected count? I'm actually going to exponentiate. Okay, I'm going to exponentiate that. Okay, when I exponentiate that, the 18.9 that I got actually mean the expected count of the customers in the baseline group. That's all it mean. Okay. And you know what? The baseline that we just talked about does not make sense. You know, how do I expect to have a customers in my store when the housing, when there's no housing in the region, when the income is zero, when age is zero, when the distance to the nearest competitor is zero, when average distance, to the store is zero? That doesn't make sense. Having customers, of course, you know why we use intercept. At times, the interpretation of intercept may make sense or not. It doesn't really matter. Okay, and that was why I said it may be helpful to center our covariate, but this is not a big deal if we don't care about baseline, because our primary inference is about the increase with respect to covariate. So what I'm trying to tell you, our major interest is not on the intercept. Our major interest is on the contribution of the covariates. What are the covariates that am I talking about? Talking about housing. What is the role of the housing? What is the role of the income? What is the role of the age? That's exactly what we mean. Okay. Now, how do we now interpret beta 1? Okay. You're going to say, as the increase in the log expected count, okay, or the log rate ratio comparing districts whose numbers of housing unit differ by 1. Okay, don't forget the X1 is actually housing. You see that? It's housing, right? When you want to say when increase, if there's a unit increase in housing by 1, don't forget that. So, and that's exactly what we mean. So right here now, okay, adjusting for other covariate, don't forget, there are other covariate like income, age, and so on like that. Okay, so that is how you're actually going to interpret the beta 1. And if you want to go by, if you don't want to use the log expected count, I told you, if you want to remove the log, we're going to exponentiate. Okay, exponentiating that will lead us to this guy. How are we going to interpret this guy? That is the rate ratio comparing districts whose mean housing unit differ by 1, adjusting for other covariates. You see the difference between the two? We did something like that also in logistic regression, where when you want to go from the log odd to odd, we exponentiate. Okay. And the log odd, you're going to have its own interpretation. The log odd estimate will have its own interpretation. The odd ratio is also going to have its own interpretation. The same thing we're doing here. Okay, now, we may want to go to a situation that is going to make sense, more sense. You know why? When you take a look at this guy here, we're only focusing on a unit increase in housing. Like when in a region, when the housing increased by 1. But that is too small. We can consider situation where, it go up by 100. Look at this. If you compare this guy, this is for 1, right? Differ by 1. But if you want to talk about this one is a differ by 100, you're comparing district now. A particular district has 100 more housing than another district. That's what we're talking about here. All what you're going to do is to multiply 100 by the beta 1 before you exponentiate. And what will this guy, how is this guy interpreted? So this guy is going to be interpreted as the rate ratio comparing district whose mean housing unit divided by 100. Do you know I can also ask you to do the 1 divided by 1,000? If you want to do divide by 1,000, all what you're going to do, you could put 1,000 there, multiply by beta 1, then exponentiate that. Okay? And you know what this guy mean? Okay? This is an increase. because if you multiply this by 100, that is going to be more than 100. And that's why we say keeping other factor constant, a 100 unit increase in housing unit will yield an expected 6.2% increase in customer account. Where do I get 6.2% from? Okay, from here, look at that. If you multiply by 100, that's multiplied by 100 is basically going to be 106.2. 106.2. If you subtract 100 from that, that will be 6.2 increase. Take a look at that. Okay, so this actually favor region with more housing because there's going to be 6.2 increase in customer account. Okay, so take a look at that. Okay, now the next one now is you can also go all the way to interpret the other predator. Okay, look at C from the log or expected count all the way to the expected count, just like the same way I did for housing. Okay, now if I want to test this for significance of a particular predator, okay, I'm actually going to use Z statistic. Okay, what I'm trying to say in a sense is if you take a look at the 4.26, okay, I need you to come here. Do you see this guy? Oh, give me 1 second. Do you see this guy? That is a Z value. If I want to test the significance of the housing, okay, and I got this guy by doing this guy divided by this guy, which is equal to this guy. What is a p-value? This is a p-value. This is what we use to take a decision at the end of the day. So that's exactly what I'm just trying to say. Okay, now that's what I'm trying to say here, that we're actually using a Z statistic. Now let us go ahead and interpret the beta 2. Don't forget, the beta 2 is the one that has to do with the income. Okay, for beta 2, okay, we're going to mention increase in the log expected account or the log rate ratio comparing district whose mean income divided by $1. Okay, and if you want to remove the log, you're going to do the exponentiation. Don't forget, okay, the exponentiation now basically going to be relative rate comparing regions whose mean income divided by $1, adjusting for other covariate. Oh my God, always mention adjusting for other covariate. You remember we did the same when the numbers of predator is more than 1. You got to adjust for other covariate, like keeping them at constant. Okay, now you know, oh my God, the $1 okay, somebody said I have to leave early. That's no problem. Okay, now if you take a look at what I have now, the $1 is very small. The same way I did to housing, I can also do it to the income here too. The $1 here increases, you know, is very small. I can say, okay, what about 10,000? Don't forget, we're talking about district, right? Okay, for 10,000 now, okay, increase. No, I'm just going to do 10,000 multiplied by the estimate, and that will give us 0.889. Okay, you know, the 0.889, okay, this is, if you multiply by 100, this is going to be less than 100, 88.9. Okay, and that was why I said this is the relative rate comparing region whose mean income differ by 10,000, adjusting for other covariate, which means keeping other factor constant. The relative rate comparing region whose average income differ by 10,000 is this. That is a relative income. Okay, and what does that mean? It means for a $10,000 change in an average income, okay, we'll predict 11% decrease. How do I know 11% decrease? Is because of this guy. Multiply by 100, that's 89.9, right? 88.9, right? What is 100 minus 88.9? That's 11% decrease. Okay, and the word decrease, don't forget, you see a negative, right? Okay, because that was actually what we got when you come back here. When you come back, okay, give me 1 second. I'm going to clean that one out. Okay, so take a look at this. We're talking about income. Okay, you see negative. Okay, that was why that was a decrease. Okay, so that is how to interpret that. I've just used the 10,000 now. Okay. Now we can also find the confidence interval. Okay. Now, if I want to find the confidence interval for beta 1, for beta 2, for beta 3, and so on like that, is what I can do. Okay. This is a formula for 95% confidence. Beta 2 curve, plus or minus, the 1.96 is going to be the z-score, the z value. Okay. And the standard error here is actually is here. You're going to see the standard error in the table. Give me 1 second. The standard error is actually, can you see this guy? For whatever you want to do, that is the standard error. You see this guy, right? Okay. So that is going to be the standard error. So take note of that. Okay. So now using the standard error now, I can actually take a look at that. This is what I'm actually going to get. Okay. For the income, I can do this for housing. And if I got this for the income, don't forget, we're talking about the log. Removing the log, I can exponentiate this. Exponentiating the confidence interval. You see what I've done here? Exponentiating now, this is what we're going to have. You see that? Okay. And if you want to talk in terms of $10,000 difference, okay, you're just going to put $10,000 and you want to talk about the confidence interval for that. That is exactly what I'm doing here. So take a look at that. Okay. Now, this is interpretation now. Okay. If I basically want to interpret this guy, okay, take a look at that. Okay. The 95% confidence level for the relative rate for customer visiting, okay, visiting the store is this. For a $10,000 increase in average income for the region, don't forget that, I'm actually interpreting this guy now based on the $10,000 difference. Okay, what about if I ask you to do that of $1,000 difference or $100 difference or $1 difference? Okay, the $1 difference is this guy here. You see the $1 difference? Okay, the $1, there's a 1 here, right? Okay, there's a $10,000 difference. Okay, and this is for the log expected, but this is expected. Take a look at that. There's a difference between the log expected count of the customers and the expected count of the customers. Okay, now the question now, based on this model, if we are going to choose a location to build a new store, should we choose area with higher or lower income? Or does it matter? I needed to answer that. You can take a look at what we've done. Okay, you want to site a location, you're looking for a location where you want to site your store. Are you going to consider, based on what we have now, based on this result now, are you basically going to consider a district with a higher income or lower income, or does it matter? So that depends on you understanding what I just presented now. Okay, I want to go into the summary of what I've presented today. Like I said, Poisson regression gives us a framework to build models for count data. When the nature of the response is a count, okay, it's a count, you're actually going to use Poisson regression. And it is a special case of a generalized linear model. And therefore, it is closely related to linear and logistic regression model. Okay. And I say all of the same modeling technique we carry over from linear regression. Adjustment for confounding. What do I say? Well, we are adjusting for confounding if I'm looking at the effect of housing on the numbers of customers that will visit my store. And I'm also incorporating other effects as well. Okay, other effect like the income, age, and stuff like that. That is adjusting for confounding. Okay, then also allowing for the effect of modification by feeding interaction. Today, we have not fed interaction. Okay, the idea of interaction can also be brought in a Poisson regression model. Okay, don't forget, we can think of interaction in a situation where the effects of a particular predator on the response depend on another predator. Maybe, for instance, effect of housing on the numbers of customers visiting my store may depend on the income. What about that? Because of that, we can be thinking of, you know, uh, you know, considering interaction effect. Then we can also, you know, look at other polynomial model. We can also talk about polynomial model within the Poisson regression framework. Okay, now the idea of Z statistic was used in testing significance of the predator in a Poisson regression model. Okay, and we can also do likelihood ratio tests that we did in the other regression type model, where we compare a complicated model with a simple model. Okay, and we can also have a way to interpret the parameters of the regression or the Poisson regression model, starting from the intercept to every other one. And we also have a way to, you know, get rid of the log. Okay, when we want to talk about the expected count by exponentiation. Oh my God, this is going to be the end of my lecture. Is there any question? Is there any question? Now, if you really understand what I've passed across today, I need you to say yes or comment yes, or you give me a thumbs up. If you really understand what I've, oh my God, all of you actually understand that, but you know what, if there's anyone among you who doesn't understand, okay, make sure you ask question or you text, you know, you meet with me during my office hour. Of course, you know, my office hour is actually start 11:30. Okay. You know, and for those of you who have reading the makeup, you know, midterm one, your results is going to be uploaded today because, you know, I have some guys that actually wrote makeup to the midterm one. And of course, for the midterm two, the practice question is basically going to be uploaded today. Okay. And you're actually going to have the opportunity to see the area the midterm two is going to cover. And of course, information, detailed information about the conduct of the midterm two will also going to be released today. So like I said, I really, let me say, I really want to appreciate everyone for attending my lecture today. The emergency is now being under control. Of course, I'm actually going to return to in-person teaching tomorrow. Okay, see you in class tomorrow. Bye for
So,
now, everyone.
d-
Okay, go
do we
ahead.
s- do we still have the exam from Friday to Saturday this week?
Confirm, yes. We
Okay,
still have it.
thank you.
So, like I said, there's gonna be a follow-up information about that today. Make sure you check the announcement section of the canvas for detailed information. So my answer to that is actually yes. Any other question before I go? Okay. In the absence of question, uh, make sure you all stay safe and have a very good day. Bye for now, everyone.